We continue to work with limits of sequences, and in a previous video we looked at how limits respect the various algebraic operations. So the limit of a sum is the sum of the limits, limit of the product is the product of the limits, etc. Here we look at how limits respect the ordering of the real numbers. So if two sequences satisfy a less than or equal to relation, when you look at them term by term, this relation carries over to their limits. A special case of that fact is the following, which will be our warm-up. If we have a convergent sequence, all of whose terms are bounded below by m, then the limit is also bounded below by m. A very intuitive and predictable result, once again one that requires a proof. And as straightforward as this proof is, it's a stepping stone for more ambitious proofs. Let's do this proof by contradiction. Suppose the sequence converges to a limit a which is less than m. Eventually, all the terms of the sequence will have to be close to a and therefore less than m, and that should give a contradiction. Now let's try to translate that idea into an actual proof. The first thing is, instead of just saying close to a, we'll have to say how close. And apparently it's within this distance epsilon, which I'll take to be m minus a. Now by assumption, the sequence is also approaching a. So there's some capital N such that for all little n bigger than capital N, the terms of our sequence are all within epsilon of a. For all such little n bigger than capital N, a sub n is less than a plus epsilon. But that's the same as m. And now that contradicts all terms being greater than m. The contradiction completes our proof. But here's a slightly different wording of the same thing. It's acceptable and slightly shorter. Instead of introducing a new letter, capital N, all we really need to say is that for all sufficiently large little n, the terms of our sequence are all within epsilon of the limiting value of a, which gives the terms of the sequence to be less than m, and that's our contradiction. Let's add a second part to this theorem, which works just like the first part. If a convergent sequence is bounded above by m, then the limit is also less than or equal to m. And for reasons we explained before, the first few terms of the sequence don't affect the limit, so we could weaken the hypotheses slightly, get the same conclusion. We don't really need the bound to hold for all terms of the sequence, just as long as the bound holds beyond some point in the sequence. Here's the more general fact which I mentioned at the start of the video. If we have two convergent sequences, where the first sequence is term by term greater than or equal to the second, then the same relation holds for their respective limits. To prove this, we make our lives easier if we use some stuff we've already proved in the earlier video. We can take our two sequences and add or subtract them term by term to get a new convergent sequence. If we subtract, then by hypothesis, the sequence of differences has terms which are non-negative, and the limit of this sequence is a minus b. Okay, so just a quick word about this. I showed you what happens before when you add or multiply two sequences term by term. And what happens when you subtract? That should follow without explicit mention, but if you do need the explicit details, here they are. The constant sequence with terms -1 converges to -1. That's easy enough. If we multiply that sequence term-wise by the sequence of bn's, we get a sequence of minus bn's by the earlier result. the sequence converges, and for its limit, you just multiply -1 times b and get minus b. Now the sequence of an minus bn is now just a sum. It's a sum of two sequences with terms an and negative bn. So you just add their limits, you get a minus b. Now, by the first theorem in our video, this video, for a convergent sequence with non-negative terms, the limit must also be non-negative. This says a minus b is non-negative. Oh, well that says a is greater than or equal to b. QED. Now, let's prove this form of the squeeze theorem. Again, something you must have heard about in calculus, and you must have used many times without proof. Now we get to prove it. Take three sequences with terms an, bn, and cn. We suppose the terms of the second sequence are trapped between the terms of the other two sequences, as shown. If the first and third sequences converge to the same limit, then the middle sequence must also converge to that same limit. We can't assume this sequence of bn's converges. We have to prove that. It's not clear how to conclude this directly, just using our previous statements of previous theorems, so we do need to go back to definitions with this one. So let epsilon be positive. For all sufficiently large n, the an's and cn's are all within epsilon of the same limit L. You could say there should really be some n1 for the first inequality and an n2 for the second inequality. I'll explain that point shortly, but let's proceed the way we're going here. For such values of n, we have this lower bound for an, it's from the first inequality. And then we can stick in those other inequalities that come from our hypothesis. And then finally add on an upper bound for the cn, which comes from the previous line. Now you see we have bn trapped between L minus epsilon and L plus epsilon, which really says for all sufficiently large n, bn is within epsilon of L. So that's exactly what we wanted. Now let's explain the details about using an n1 for the first inequality and an n2 for the second inequality. You end up taking little n to be greater than the maximum of those two n's in order to make everything work. There's no need to explain all this in full detail once you're comfortable with it, but if you feel the need to spell it out, if you want to ramp up more slowly in writing your proof, then that's good. So far, we've talked about convergent sequences, which are sequences converging to some number. Now we can also talk about sequences which go to infinity or to minus infinity. Here's what it means for a sequence to, quote, go to infinity. It just means we can make the terms of the sequence as large as we want by just going far enough out in the sequence. Beyond some point, all the remaining terms bigger than 100. Then beyond another point, all the remaining terms are bigger than 1,000,000, and so on. I've written the definition here. You should please note everything here in the definition is about actual numbers. There's nothing infinite here. The lazy 8 symbol, which we use as a shorthand, that's all it is. It's just a shorthand for this definition. Here is an alternative way to write the same thing, the same limit. This notation is possibly more typical in calculus textbooks. And then there's this other variation. I've dropped the parentheses because it should be clear from the context now. If I say little n is going to infinity, then a sub n is a sequence depending on that little n, so I no longer need parentheses if I spell it all out this way. And whichever notation you use is usually depending on where you put it in a sentence, just to make the sentence flow better, and possibly for variety in the way we write things. You should get used to using this different notation. And we can mimic all of the above for sequences going to minus infinity. Please note that if a sequence goes to plus or minus infinity, then the sequence is unbounded, so the sequence must diverge. The converse, however, is not true. There are sequences which diverge, but which do not go to plus or minus infinity. Think about that. Pause the video if you need to. Similarly, a sequence can be unbounded without going to plus or minus infinity. There are simple examples to illustrate these phenomena. Think about the sequence 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, ... It's unbounded, but it does not go to infinity. In thinking about sequences, you should be guided not just by theorems, but by examples, often very simple examples. It's very important to test statements against the simplest examples you know, so that you don't fall into any obvious gaping traps. Having just proved a version of the Squeeze theorem for convergent sequences, we can mention there are several other forms of the Squeeze theorem which are not hard to prove. We won't take time to go through every possible variation. But for example, suppose an is less than or equal to bn for all n. If the first sequence goes to infinity, then so does the second. That's another form of the Squeeze theorem.